qualitative analysis of organic compounds means that in an organic compound, we are going to determine which all elements are present. We are going to detect the presence of carbon and hydrogen. So what do? We take the organic compound and react it with copper oxide. What is this yellow precipitate? It is ammonium phosphomolybdate. So if there is a yellow precipitate that you are obtaining, we can confirm the presence of phosphorus. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So in the last session, we discussed about the methods of purification of organic compounds, right? So based on the nature of the organic compound and the impurities, we use the appropriate method of purification, right? So we studied about distillation, sublimation, crystallization, differential extraction and chromatography in detail in last session, right? So in today's session, we are going to study about the qualitative analysis and quantitative analysis of organic compounds. Right. So let's begin with the first one, that is qualitative analysis of organic compounds. So from the word itself, we can determine what we are going to study here. Qualitative analysis, quality, or that means that qualitative analysis of organic compounds means that in an organic compound, we are going to determine which all elements are present. So organic compounds means we know that it contains carbon as well as hydrogen. So apart from carbon and hydrogen, if there are any other elements also present, we determine it using qualitative analysis of organic compounds. So as the name suggests, qualitative, we will be only detecting the elements present in the organic compound. If carbon is present, hydrogen is present, nitrogen, sulfur, phosphorus, halogens, if these elements are present or not present, we'll determine using qualitative analysis. Then comes quantitative analysis, in which after the detection of the elements, we will be understanding or we will be calculating the amount of carbon present, how much carbon is present in the organic compound, how much hydrogen is present, how much of nitrogen is present, like that. Okay, so that is the difference between qualitative and quantitative analysis. So beginning with qualitative analysis, as said, we will be detecting the different elements which is present in the organic compounds. So as I said, it is not necessarily always carbon and hydrogen which is present. There can be other elements as well present. So let's study in detail about that. Okay, so first we are going to study the detection of carbon and hydrogen. Right, the detection of carbon and hydrogen in organic compound by the copper oxide test. So as the name suggests, copper oxide test, we will be reacting our organic compound with copper oxide. So let's see what happens. The organic compound is mixed with dry copper oxide, and the mixture is strongly heated in a hard glass test tube fitted with a cork and a delivery tube. The liberated gases are passed into lime water, and carbon present in the compound is oxidized by copper oxide to carbon dioxide, which turns lime water milky. So what is happening here? So we are going to detect the presence of carbon and hydrogen. So what do? We take the organic compound and react it with copper oxide, right? So the carbon reacts with copper oxide and produces carbon dioxide, right? It produces carbon dioxide, and when this carbon dioxide is passed through lime water, what happens to the lime water? It turns milky, right? It turns milky. So if the lime water is converting, or if the lime water color changes to milky, right, what we can confirm? The presence of carbon. And how do we confirm the presence of hydrogen? When hydrogen is also present in the organic compound, yes, when it is reacting with copper oxide, right, it forms water, right? Now, when the water is further reacted with anhydrous copper sulfate, it reacts with water and formed copper sulfate 5H2O, which will have a blue color. Okay, so based on this, we can detect the presence of carbon and hydrogen. So let's see in detail. When carbon is reacting with copper oxide, it produces carbon dioxide. Okay, so if carbon is present, it reacts with copper oxide and produces carbon dioxide. So to detect whether carbon dioxide is itself the gas which is present there, this carbon dioxide is made to react with calcium hydroxide, that is lime water, right? It is passed through lime water, and if the lime water turns milky, we can confirm the presence of carbon, right? In the same way, how to confirm the presence of hydrogen? If hydrogen is made to react with copper oxide, it forms water, right? Now, when the water is passed through anhydrous copper sulfate, that is, now the anhydrous copper sulfate will be white in color, right? It doesn't have any color. So when the water is passed through anhydrous copper sulfate, if it forms a blue color, then we can confirm the presence of water as well. That is, confirm the presence of hydrogen. So this is how we determine the presence of carbon and hydrogen using copper oxide test. Right? Now moving on to the next one, that is detection of nitrogen, halogen and sulfur. So as said in the beginning, it's not necessarily always carbon and hydrogen. There can be other elements as well. So we are going to detect the presence of nitrogen, sulfur and halogen. So together, to detect the presence of nitrogen, sulfur and halogen, we use the Lezaine's test. Yes, Lezaine's test is what we use. That is basically sodium fusion extract test. You can also say it as sodium fusion extract test. Alright. So Lezaine's test is used to detect the presence of nitrogen, sulfur and halogens. So what is this sodium fusion extract? Okay, so first we need to prepare sodium fusion extract, then we will continue with the further reactions to detect nitrogen, sulfur and halogens. So let's now see how to prepare the sodium fusion extract, right? So a piece of dry sodium is introduced into a fusion tube and heated till it melts. Okay, so we take a fusion tube, which is a very small glass tube, right? It's a very small glass tube in which we take a very small piece of dry sodium. We put in a small piece of sodium into that, right? And then a drop or few crystals of organic compound is added to the fusion tube. Now in the fusion tube, we have a small piece of sodium. Now to this fusion tube containing the sodium, we add few drops of the organic compound, which we have to detect the elements, right? Now to this, we add the organic compound as well, few drops of it. Now what do we do? The mixture is fused gently on a Bunsen flame initially. We start heating it, okay, using a Bunsen burner, right? Now the tube is then heated to red hot and plunged into distilled water taken with a mortar. So that means now my fusion tube is containing the sodium as well as the organic compound. Now the mixture of it we start heating and it has to become red hot, right? It has to become extremely hot, and then we take a china dish in which distilled water is present. So once it becomes red hot, directly this glass tube will put it inside the water, the distilled water. So what happens? Extremely hot substance, we are putting it inside water, the glass will break, right? Yes, and now what we do? We grind it thoroughly, right? The contents are grounded thoroughly and filtered, okay? So once we put it into the distilled water, the glass breaks, right? The mixture will be now present inside the water. So now we grind it thoroughly. That is, the glass pieces and the organic compound, we grind it thoroughly and then we filter it. Right? Once we filter it, the glass pieces and other impurities will remain in the filter paper and we get the filtrate which is containing the sodium fusion extract, right? So, the filtrate is then divided into three parts. When the organic compound is fused with sodium, nitrogen, halogen and sulfur are converted into sodium cyanide, sodium halide and sodium sulfide respectively. What does that mean? Now, the filtrate that we are getting, it is not just sodium, that is sodium plus the organic compound, right? So, if the organic compound is containing nitrogen, yes, carbon and nitrogen, what will be formed? Sodium cyanide will be formed, NaCN, right? And if the organic compound is containing sulfur, sodium sulfide will be formed, right? Sodium sulfide will be formed. And if the organic compound is containing halogen, sodium halides will be found, NaX. Okay, so now the filtrate will be containing this form of or this particular compound, that is either sodium cyanide, sodium sulfate or sodium halides, right? I hope it is clear. So this is how we prepare the sodium fusion extract. So this is the first step. Now from that is with the sodium fusion extract, we will continue the further reaction. So first we are going to study the detection of nitrogen. From the sodium fusion extract that we have prepared now, we are going to test the presence of nitrogen. Okay, so a few crystals of ferrous sulfate are added to a small amount of the filtrate. So now what is present in the filtrate? Yes, it will be sodium carbon plus nitrogen will give sodium cyanide. So now this sodium cyanide is present in the filtrate. Now the sodium cyanide, I am reacting it with ferrous sulfate. Okay, right? The mixture is boiled and then cooled. It is acidified with hydrochloric acid and few drops of ferric chloride solutions are also added. Right? So the sodium cyanide is reacted with ferrous sulfate. That is the reaction that you can see. Right? Sodium cyanide is reacted with ferrous sulfate, which is shown by Fe2+, right? And NaCN is shown by Sn- ion, right? Okay, so the sodium cyanide is reacted with ferrous sulfate and then further it is acidified with hydrochloric acid and ferric chloride, right? And then the sodium cyanide in the filtrate reacts with ferrous sulfate to give sodium ferrocyanide. Okay, sodium cyanide reacts with ferrous sulfate first and forms sodium cyanide. Now it further reacts with the ferric chloride to give Prussian blue or green colored solution of ferric ferrocyanide. Okay, so the compound that you are obtaining here is called as ferriferrocyanide, which will be Prussian blue in color. So once you do this reaction, if you are obtaining a Prussian blue color, we can confirm the presence of nitrogen, right? So I'll repeat once again. Yes, the sodium cyanide, first we'll react it with ferrous sulfate, right? And then we will further acidify it with hydrochloric acid and then add ferric chloride to it. And finally, if you are obtaining Prussian blue color, we can confirm the presence of nitrogen. Okay, so this is the test for nitrogen. Now moving on to the next one, that is test for sulfur. Okay, there are two tests by which you can detect or confirm the presence of sulfur. The first one is a small amount of the filtrate. Now what is contained in the filtrate? Yes, sodium plus sulfur will give sodium sulfide, right? Now the filtrate is containing sodium sulfide. Okay, now the sodium sulfide is treated with excess of acetic acid and lead acetate solution. Excess of acetic acid is added first and then to that we'll add lead acetate solution. Yes, and a black precipitate of lead sulfide is formed. Okay, so once you do the reaction and if you are getting a black precipitate, that means we can confirm the presence of sulfur. So what is actually the reaction happening here? Yes, the sodium sulfide, when it reacts with lead acetate, which is shown by Pb2+, lead acetate, you will get a black precipitate. What is this black precipitate? Lead sulfide, PbS. This is the black precipitate. So if you are getting a black precipitate, we can confirm the presence of sulfur, right? I said there is one more test, that is to a small amount of sodium fusion extract, sodium nitroprusside solution is added and appearance of color confirms the presence of sulfur. What color? A violet color will be obtained, right? So the sodium fusion extract contains the sodium sulfide, right? So now the sodium sulfide, if you are reacting it with sodium nitroprusside, this is sodium nitroprusside, we will get a violet color. Yes, as you can see, it is just NO here and it is NOS here, right? So the sulfur is also present in the product. Okay, so the color changes to violet. So once this reaction is done, if you are getting a violet color, yes, we can confirm the presence of sulfur. So now if our organic compound is containing both nitrogen and sulfur, how do we detect it? Yes, we studied the detection of nitrogen, studied the detection of sulfur separately. Now if both are present in an organic compound, how do we detect it? Let's see. If the organic compound contains both nitrogen and sulfur, then the extract gives blood red color, right? Instead of getting a Prussian blue color, we studied it in the detection of nitrogen, right? So instead of getting a Prussian blue color, you will be getting blood red color because of the presence of sulfur as well. So when it reacts with ferric chloride due to the formation of ferric thiocyanide. Okay, so that means now the sodium fusion extract will be containing sodium thiocyanate, right? Na, that is sodium, carbon, nitrogen and sulfur. Nitrogen and sulfur is present. So instead of getting sodium cyanate, you will have sodium thiocyanate. Sulfur will be also present, right? So now when this sodium thiocyanate reacts with ferric chloride, instead of getting Prussian blue color, you will get a blood red color, right? So if this is when there is sulfur as well as nitrogen present in your organic compound, right? So this is the detection when both of them are present. Instead of Prussian blue color, you will get blood red color. Right? Now moving on to the next one, that is test for halogens. Halogens, we will be testing chlorine, bromine and iodine. Okay, chlorine, bromine and iodine. So in the sodium fusion extract, if chlorine is present, your sodium fusion extract will be containing sodium chloride. If it is bromine, NaBr. If it is iodine, NaI. Right. So how do we detect it? Let's see. A small amount of the filtrate. So now the filtrate can contain sodium chloride, sodium bromide or sodium iodide, right? Is treated with dilute nitric acid followed by silver nitrate solution. Okay, so we'll be taking the sodium, whichever halogen is there, sodium chloride, sodium bromide, sodium iodide, that is the filtrate, and then we add dilute HNO3 first, that is dilute nitric acid, followed by silver nitrate, we get a precipitate. Now based on the color of the precipitate and the characteristic of the precipitate in ammonia solution, we will be able to detect it whether it is chlorine, bromine or iodine. So let's see. Now the formation of white precipitate, that is if a white precipitate is formed, that means it is actually silver chloride. Okay, so when you do this reaction, you will be obtaining silver halide. It can be chlorine, bromine or iodine. Okay, so if you are getting silver chloride, that means if it is chlorine which is present, you obtain a white precipitate which is soluble in ammonia hydroxide. It indicates the presence of chlorine. So that means sodium chloride. If chlorine is present, when it reacts with silver nitrate, you will get the NaNO3 and silver chloride. So this silver chloride, which is a precipitate, white precipitate, indicates the presence of chlorine. And this white precipitate, that is silver chloride, will be soluble in ammonium hydroxide. Now on the other hand, the formation of a pale yellow color. If it is a pale yellow color, yes, the compound formed will be silver bromide, right? And this will be sparingly soluble in excess of ammonium hydroxide, right? So if it is bromine, you will get a pale yellow color which is sparingly soluble in ammonium hydroxide. And now if it is iodine, you will get a deep yellow color which is insoluble in excess of ammonium hydroxide. Okay, so if it is chlorine, you will get a white precipitate which is soluble in ammonium hydroxide. If it is bromine, you get a pale yellow color which is sparingly soluble in ammonium hydroxide, and if it is iodine, you get a dark yellow color which is insoluble in ammonium hydroxide. So in this way we can detect the presence of chlorine, bromine and iodine. Now when nitrogen or sulfur is also present in the compound apart from halogens, if there is nitrogen as well as sulfur present in the compound, the sodium extract before testing for halogen is boiled with strong nitric acid to decompose the cyanide and sulfide formed during the sodium fusion. That means if the organic compound contains halogens as well as nitrogen and sulfur, to detect the presence of halogens in it, first we have to decompose or we have to remove the nitrogen and sulfur from it. We have to decompose it. So how do we do that? We have to react it with strong nitric acid. If not removed, these radicals will form a white and black precipitate respectively on the addition of silver nitrate. Right? Instead of getting white or pale yellow or dark yellow color, you will be getting black or white precipitate. Right? So first what we have to do, we have to react the sodium fusion extract with HNO3. right, with nitric acid. Either if it is cyanide, it has to be decomposed, and if it is sulfur, it is present, H2S will be decomposed, right? So first, the decomposition of the sodium cyanide and sodium sulfate must be done. Then only we can continue with the reactions for halogens, right? Okay. Now, the last one is detection of phosphorus, right? We study the detection of nitrogen, sulfur and halogens using sodium fusion extract, which is called as the Lazar's test, right? Now, the next one is detection of phosphorus. A small amount of the extract on heating with sodium peroxide. So, we are reacting the extract with sodium peroxide, which gives sodium phosphate. As you can see, it gives sodium phosphate first. Now, this on boiling with nitric acid followed by the addition of ammonium molybdate gives a yellow color or precipitate of ammonium phosphomolybdate, right? And this confirms the presence of phosphorus. Yes, so the extract first reacts with sodium peroxide, which forms sodium phosphate, and sodium phosphate is further reacted with nitric acid and you will get phosphate here, right? And this, when it is further reacted with ammonium molybdate, yes, when it is reacted with ammonium molybdate, finally you will be obtaining a yellow precipitate. Yes, what is this yellow precipitate? It is ammonium phosphomolybdate. So, if there is a yellow precipitate that you are obtaining, we can confirm the presence of phosphorus, right? Okay, so I hope the detection of nitrogen, phosphorus, sulfur and the halogens is clear for you, right? So, this is the qualitative analysis of organic compounds. We detected the elements present in the organic compounds. Now, we are moving on to the quantitative analysis. So, now we know which all elements are present in the organic compound, whether nitrogen, sulfur, oxygen, the elements which are present is clear for us. So, now we need to know about how much amount of nitrogen is there, how much carbon is there. That we will determine using quantitative analysis of organic compounds, right? So, the determination of the percentage composition of various elements present in a compound is known as quantitative analysis. So, in the whole of the organic compound, how much carbon is there? How much nitrogen is there? How much hydrogen is there? That is the amount or the percentage of this we will calculate using quantitative analysis. Okay, so the first one we are going to see here is the estimation of carbon and hydrogen. We are going to calculate how much amount of carbon and hydrogen is present in the organic compound, and this is done using Liebig's test. This is done using Liebig's test. Okay, so this is a very important test. Okay, so let's see how this works. A known mass of organic compound is heated in the presence of excess oxygen and copper oxide. The carbon dioxide and water formed are collected and weighed. The percentage of carbon and hydrogen in the compound are calculated from the masses of carbon dioxide and water. So that means a known mass of organic compound. We take the organic compound and it is heated in the presence of pure oxygen, yes, and copper oxide, right? And carbon dioxide and water will be formed, right? When the organic compound containing carbon and hydrogen is reacted with copper oxide, it forms carbon dioxide and water, right? Yes, and they are further collected and weighed, and then the percentage of carbon and hydrogen in the compound are calculated from masses of the carbon dioxide and water formed. Right. So now let's understand the procedure in detail. Right. So the sample of an organic compound is weighed accurately and it is placed in a porcelain boat in the combustion tube. So as you can see in the apparatus which is shown here, there is a combustion tube which you can see, right? And here in this position, that is the organic compound is kept in a platinum boat. Why platinum is used? Because it doesn't react with oxygen, right? Okay. Yes. So in a small platinum boat, we keep the organic compound inside the combustion tube. This is the first step, right? Now, two adsorption U tubes containing anhydrous calcium chloride and concentrated solution of potassium hydroxide respectively are weighed and connected to the combustion tube, right? So this part is clear. Now as you can see, there are two U tubes which is present here. Yes, one contains anhydrous calcium chloride and the another U tube contains potassium hydroxide solution, right? Calcium, anhydrous calcium chloride and potassium hydroxide solution. So before fitting it with the apparatus, you have to measure it. right? We take out this from the apparatus, measure how much anhydrous calcium chloride is present before beginning the experiment, right? And then same way we have to measure the amount of potassium hydroxide solution also present before starting with the experiment, right? Once the measuring of anhydrous calcium chloride and potassium hydroxide solution is done, now we fit it with the apparatus, right? Now the combustion tube is heated. Now we start heating the combustion tube. Pure and dry oxygen is passed into the combustion tube. Now once all the apparatus is done, that is the fitting of the two U tubes is done, we start passing pure and dry oxygen through the combustion tube. So the oxygen now will pass through the organic compound, so through this combustion tube. We start heating it and we pass the pure and dry oxygen through it. Right. Now, water and carbon dioxide formed are led to the absorption tubes and weighed. The increase in the masses of the absorption tube give the mass of carbon dioxide and water. That means, as the oxygen is passing through the organic compound, now the organic compounds will pass through the combustion tube and it will reach this U tube. Right. So, as I said, when it passes through the copper oxide which is present here, the carbon forms carbon dioxide and hydrogen will form the water, right? So now after it passes through the combustion tube, now carbon dioxide and water will be formed. Now if the carbon dioxide is passing through the first U tube, no much reaction takes place, and if it passes through the second U tube, what happens? The carbon dioxide will be absorbed in the potassium hydroxide solution, right? And one more product is formed here. What it is? It is water. So now when water is passed through anhydrous calcium chloride, right, what happens? It is absorbed in the anhydrous. It is anhydrous, right, without water. So now water comes, it absorbs it, right? So in this U tube you will be obtaining water, and in this U tube you will be obtaining your carbon dioxide. Now once the reaction is complete, what we'll do, we'll take out the both of this U tube and then again weigh it. Right. So initially what was the weight and finally what was the weight? When we take the difference, we will obtain the mass of hydrogen and carbon dioxide which is deposited in the U tube. Right. I hope it is clear. So if initially CXHY, this is the organic compound, it reacts with pure and dry oxygen and it forms carbon dioxide and water. Carbon dioxide will be obtained in the second U tube which is containing potassium hydroxide solution, and water will be obtained in the first U tube containing anhydrous calcium chloride. If we take the difference between the masses initially and finally of the two U tubes, we will obtain the mass of carbon dioxide and water. I hope it is clear. Right. So now how to do the calculation? We obtained the masses of carbon dioxide and water now. Right. So from the carbon dioxide and water which is formed, that is from the masses of both of it, we need to understand or calculate the mass of carbon and hydrogen. That is our aim. Right. So how to do the calculations? Let us see. So if we are considering the mass of the organic compounds as S gram, right, the mass of the whole of the organic compound is X gram, and mass of carbon dioxide which is obtained is A gram, right? First we are going to calculate the mass of carbon in carbon dioxide, right? So if the mass of carbon dioxide is A gram, right, 44 gram of carbon dioxide contains 12 gram of carbon. So carbon dioxide, yes, one molecule of carbon dioxide contains 44 gram, right? How 44 gram? Carbon 12 and oxygen 32. You will get 44 grams. So out of this 44 grams of carbon dioxide, how much gram of carbon is present? 12 gram of carbon is present, right? Rest 32 is oxygen, right? So that is written here. 44 gram of the carbon dioxide contains 12 gram of carbon, right? So if in that case, a gram of, yes, 44 contains 12 gram. Then if a gram of compound is present, if a gram of carbon dioxide present, then it will contain 12 by 44 into a gram of carbon, right? So if 44 gram of carbon dioxide contains 12 gram of carbon, then a gram of carbon dioxide will contain 12 divided by 44. 12 divided by 44 into a gram of carbon, right? Yes, right. So I hope that part is clear. So that if we take it as Y gram, then in general we can say X gram of compound, organic compound will contain Y gram of carbon. So if X gram of organic compound contains Y gram of carbon, 100 gram of the compound will contain Y by X into 100 gram of carbon, right? So which is the equation that you have to study here? The percentage of carbon in the compound. You can study this equation, that is mass of carbon dioxide formed divided by the mass of organic compound into 12 divided by 44 into 100. It is in percentage, so into 100. So this will give the percentage of carbon which is present in carbon dioxide, right? So the mass of carbon is obtained, that is mass of carbon dioxide formed divided by the mass of the whole of the organic compound into 12 divided by 44 into 100. Now we are going to calculate the mass of hydrogen in water. Right. So the mass of water which is obtained, let us assume that it is B gram, then 18 gram of water. Yes, hydrogen 2 and oxygen 16, total 18 gram. 18 gram of water, yes, 18 gram of water, how much amount of hydrogen is present? In 18 gram of water, you have 2 gram of hydrogen, right? 2 gram of hydrogen is present, right? 18 gram of water contains 2 gram of hydrogen. So then B gram will contain how many hydrogen? 2 by 18 into B, right? Yes, which we are considering as Z. Right. So that means X gram of your compound will contain Z gram of hydrogen. Right. So then 100 gram of compound will contain Z by X into 100 gram of hydrogen. Right. So what is the final equation for percentage of hydrogen in the compound? It is mass of the water which is formed divided by mass of organic compound into 2 by 18 into 100. So these two equations will give you the mass of carbon and hydrogen which is formed in the reaction. That in turn will give you the mass of carbon and hydrogen present in the organic compound, right? So this is the qualitative analysis of carbon and hydrogen, right, using Liebig's method, right? So let's do a numerical based on this now. 0.1 gram of an organic compound containing only carbon and hydrogen on combustion gives 0.275 gram of carbon dioxide and 0.225 of water. Okay, now calculate the percentage of carbon and hydrogen present in the compound. We have to calculate the percentage of carbon and hydrogen present in the compound, and it is given that the organic compound contain only carbon and hydrogen. So we can use Liebig's method and the calculation there, right? So the mass of organic compound is given as 0.1 gram. Mass of carbon dioxide is 0.275 gram. So we are calculating the percentage of carbon first. So what is the equation? Percentage of carbon is equal to mass of carbon dioxide formed divided by mass of organic compound into 12 divided by 44 into 100, right? So what is the mass of carbon dioxide formed? 0.275 divided by mass of organic compound 0.1 into 12 divided by 44 into 100, which will give you 75%. Yes, now we will calculate the amount of mass of hydrogen which is formed. So mass of water is given as 0.255, right? Yes, it is given as 0.225, and the percentage of hydrogen, how do we calculate from the equation? Mass of water formed divided by mass of organic compound into 2 by 18 into 100, right? So it is 0.225 divided by 0.1 into 2 by 18 into 100, which will give you 25%. So in the organic compound, 75% contains carbon and 25% of it contains hydrogen, right? So using Liebig's method and the calculation, we can calculate the percentage of carbon and hydrogen present in the whole of the organic compound. So this was the quantitative analysis of carbon and hydrogen. So in the next session, we will be studying the quantitative analysis of rest of the elements, right? So I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.